we've been talking about acids. Time to talk about bases. So here is the generic action of a base. Remember, a base is a proton acceptor reacting with water. And so the base will take a proton from water, base generically B. It will take a proton, so the formula goes up by 1 hydrogen and the charge goes up by 1. And the water, once it has given the proton away, ends up as hydroxide. So for an actual example, a classic weak base is this thing called pyridine, whose formula is C5H5N. It looks like this. It is a ring with 5 carbon atoms, a nitrogen atom, and then there's a hydrogen atom attached to each of the carbons as well. So C5H5N. Now, one of the things that you should be able to do at this point is, if you know something is an acid or a base, you should be able to predict the products of the reaction of that thing, whatever it is, with water. And so this is a base that's going to take a proton from water. So that C5H5N is going to become C5H5, and that is incorrect. I'm going to fix that. The way we usually write this will be an H here, so C5 and H plus, and we get hydroxide as well. So let's write the Kb for this process in terms of the concentration of both species. So again, just like the acid dissociation constant, the equilibrium constant for this type of reaction is, they're called Kb's, and it's just going to be Kb equals C5H5 NH plus, this will be called the pyridinium ion, times the hydroxide concentration, and then divided by the pyridine concentration, C5. And numerically, this is equal to 1.7 times 10 to the negative 9. So it is a pretty weak base. All right, so let's work through an example. So we're going to take 0.3 moles of pyridine. We're going to add it to enough water to make a liter of solution. So what are the expected equilibrium concentrations of the pyridinium, the pyridine, the pyridinium ion, H plus, and the hydroxide? So standard ice table. The pyridine, we start with 0.3 molars. Water is not going to be a problem. We have no pyridinium and no hydroxide, which means we will make some of both of these species at the expense of some of the pyridine. X molar pyridinium and X molar hydroxide. And we know what Kb is, so here it should be pretty much downhill from here. So the Kb is equal to C5H5 NH plus concentration times the hydroxide concentration divided by the pyridine concentration. Symbolically, as we've set things up, that's going to be x squared over 0.3 minus x. But given the small nature of this KB, we can make that approximation and say that this is pretty close to just x squared over 0.3, and that equals 1.7 times 10 to the negative 9, which makes the solution for x pretty easy. So we get x squared is equal to about 5.1 times 10 to the negative 10, which gives us an x equal 2.6 times 10 to the negative 5th. So get a different color here. So the equilibrium concentration of hydroxide is 2.6 times 10 to the negative 5th. The equilibrium concentration of the pyridinium ion is the same thing. And this, again, I'm going to write this out in decimal notation, 0.3 minus 1,2,3,4,2,6. So if we're obeying sig fig rules, it is actually unchanged. So we were completely justified in making that assumption. So that's a weak base equilibrium problem.